So we continue now with the last talk for the morning session by AJ Chandra, who will speak about stochastic quantization of Yang-Mills. So please, AJ, all yours.
Thanks. And thank you also to the organizers for giving me a chance to talk about some work. I'll be talking about the stochastic quantization of Yang-Mills, and I'll be talking about work is archived for 2 dimensions and work in progress in So I'll get to it. And okay, the scrolling is a little bit slow. So to begin with, I wanted everyone to know what we're talking about when we're talking about Yang-Mills. And I actually wanted to start with a little bit of a richer model, which is the Yang-Mill-Higgs model. So in order to define a Yang-Mill-Higgs model, you really start with 3 ingredients. The first one is this capital G, which is a compact Lie group. And then you have an associated Lie algebra, which I've written as mathfrak G. And then you have a vector space V, which I'm kind of suppressing it from the notation, but you should also have a representation or an action of your Lie group on V. And so each of these objects is going to give rise to a character who's going to appear in our story. So I'm just going to talk about Yang-Mill-Higgs or Yang-Mills in finite volume on a torus, in particular, like on a trivial bundle. So I'm not going to look at more exotic geometric scenarios, but then the kind of characters that we have below are a map from your domain, so this d-dimensional torus, into the Lie group. And so this is what gauge group, and it's a group just under pointwise multiplication. Then another important character is going to be the gauge field, be a G-valued 1 form on the torus. We'll call it the connection or the gauge field. And you can really think about it as just a function from the torus into GD. So the d-fold Cartesian product of the Lie algebra. And then the third character will be the Higgs field, which is just a map from the torus into our vector space. So a few more important preliminaries are that the gauge group, is a group. It has a multiplication, but it also has actions on the connections and the Higgs field. So for the connections, if we act on a connection A with G, then our prescription is to conjugate A by G, which again gives us something that takes values so conjugation by the group takes the algebra to itself. So this is all well defined. But then we have a second term here, minus dg, G inverse. And so G lives in the Lie group. This D is the exterior derivative. And so that's, if I differentiate something that takes values in the group and then pull it back to the origin, I am looking at, again, a 1 form that takes values in the Lie algebra. And then the action on the Higgs field is just basically pointwise like this. So here we're using, to be really careful, I should explicitly write down a representation here, but this is just the action of the group on the Higgs field pointwise space. So, this gauge field allows you to define a corresponding covariant derivative, which I've written here. It's a kind of combination of just the exterior derivative with a correction with another term. And here the wedge product is kind of it's a wedge with respect to the differential forms and the appropriate product. So basically, this definition can be applied to things that take values in the vector space, or if you're applying it to something that's Lie algebra valued, your product should be the bracket. And so then in the kind of one of the main characters of the story is a type of derivative of the connection, which is called the curvature. And so in terms of linking this back to, why is this a useful language for physics? Well, in principle, what you should imagine is that the connection or the gauge field is some sort of potential for a fundamental force of nature. And then the curvature is a field strength tensor. So oftentimes it's kind of simplest to explain this in the case of electromagnetism, in which case you'd want to take the connection to be a combination of the electrostatic and magnetic potential, and then F is the field strength tensor. So that F actually contains basically what the electromagnetic field is doing at every point. And so we're going to take all of these together and define an action, the Yang-Mills-Higgs action. And so what's the role of actions, right? So if you're talking about classical physics, the idea is that an action is something that you cook up so that its minimization problem gives you equations of motion for some system. So that's the case like in classical mechanics, but in classical field theory, what you should imagine is that this action is a functional, and if you minimize it, then you get equations that correspond essentially to Maxwell's equations. Now, what's important here, and what's one of the central stories in gauge theory, is that while the kind of thing that you would test in the laboratory is the curvature or the kind of the electromagnetic force, in order to kind of write Maxwell's equations as a variational problem, then what you want to do is you want to vary the potential. So writing Maxwell's equations or equations for any other force in a variational form require us to use potentials as our kind of variable. Now, this is an issue because in a certain sense, the potential is a degenerate variable when you are using it to describe physics. So given a specific curvature, there are lots of basically there are lots of different potentials that describe the same physical scenario. So for in the case of electromagnetism, you can get equivalent potentials by basically just translating by the gradient of a function. So here, the action of the gauge group is basically an action that transforms a potential into a potential that is physically equivalent. And so our action is actually fairly degenerate. So it's invariant under the action of our gauge group. So it's kind of a huge degeneracy because the gauge group is infinite dimensional. So I'm going to focus on the case of pure Yang-Mills. In our paper in the 2D model, we restricted the pure Yang-Mills, but you can without much work extend that to the model with the Higgs. In our 3D paper, we are also just treating the Higgs explicitly. And so maybe the kind of most interesting thing to say about this is that from the framework of our techniques, we don't really care about the difference, but if you look, for instance, at pure Yang-Mills in 2 dimensions, you have a lot more exact solvability compared to the model with Higgs. So that's kind of one way, and I think Ilya will talk more about this, but that's one way to contrast our approach to these models with some other approaches. But so this is the case we're going to specialize on. And so the kind of, if you build an action whose minimum gives you your equations of motion, then one way to kind of build a corresponding quantum theory is to use that action to construct a Gibbs weight. So this is the Yang-Mills Euclidean quantum field theory. And so this is how you'd formally write it, where this is some sort of abstract Lebesgue measure on connections, but this is not going to give you a probability measure. So basically, when you study 543 and you look at the 543 quantum field theory, everyone tells you, well, okay, it's a measure on an infinite dimensional space. You can try splitting it into a Gaussian part in interaction, but then you're dealing with a measure on distributions and you have nonlinear expressions. You need to renormalize. All those issues are present here, but there's another problem, which is that basically this action has an infinite dimensional symmetry. Symmetry. So then you don't expect such a thing to give you a probability measure, just because it has too many invariances. And so in some sense, the space of connections is not the right physical space. So what you'd actually want to do is look at some sort of quotient space. And in terms of physics, a class of key observables that in some sense would kind of separate points in the quotient space are traces of Wilson loops. So these are holonomies along loops. And so what's a holonomy? Well, the idea is that this gauge field, if you think of it as a connection, is something that's telling you how to do parallel transport. So given a loop that I imagine is parameterized, let's say from t equals 0 to 1, then the holonomy of my connection along that loop is given as the solution to a certain differential equation, which corresponds to basically thinking about, so you can think about the connection as telling you how to infinitesimally move in the Lie group. And so if I integrate, if I kind of solve this differential equation along a curve, I'm going to get a group element from integrating A along the curve. And so this, in some sense, gives you, it tells you how to change coordinates between the beginning and the end point of this curve. And it has a certain covariance property with respect to the gauge group, which is basically you're sort of conjugated in a sense by the gauge transformation's value at the beginning and end points. In particular, it's an actual, this is precisely just a conjugation of the holonomy if your curve is a closed loop, because then the beginning and end points are the same. And so then it's invariant under taking something like the trace. So in certain sense, these sorts of observables are what capture the actual physics. And what you'd want to do if you want to kind of calculate expectations, you only care about these guys. And in principle, what the dream would be is to actually construct the quotient space, which is the natural space to kind of define these observables on, and define a probability measure on that. Okay. So I talked about stochastic quantization. So this is, stochastic quantization in Rn. You have some probability measure given to you by some Gibbs weight. And then what you do is basically you do stochastic gradient descent, right? So you have an equation where basically you have a drift term given by the gradient of your Gibbs factor, and then you have it driven by a Wiener process. I just want to say, in order to kind of give this prescription, the key ingredient is an inner product structure on Rn that allows you to define the gradient and the Wiener process. Okay. Oh. Spurious slide. So good. So if we look at the Yang-Mills measure, then, and we kind of formally proceed along the same lines, then we would get this sort of equation. So basically just differentiating the action in the same way. And so here the equation is driven by a GD space-time, a GD valued space-time white noise. So in order to actually make this well-defined, you just need to define an inner product on your Lie algebra. But so you can, we'll assume that the Lie algebra comes with an inner product. This is the corresponding dynamic that we're hoping will help us kind of understand the corresponding measure. So our interest is, to what sense can we create a natural dynamic corresponding to this equation? One key point is that formally, if you take a gauge transformation that's constant in time, and you look at the solution of this dynamic, then, if you act on that solution with a gauge transformation, then your new connection will also satisfy an equation like this, which is of the same form, but except the noise has been conjugated by the gauge transformation. And so what's key here is, at least formally, so one of the things you'd want to do when if your inner product and your Lie algebra should be invariant under the action of the Lie group. So what you expect is that these two noises are equal in distribution. So the consequence of the gauge invariance of our action at the level of the measure is basically that the dynamic gauge covariant in law. So the issue is that if you have we had a problem when we had a measure that a measure that has too many invariances, we can't make sense as a finite measure. So we have a similar problem for the dynamic. If a dynamic has this sort of like invariance, then it's not going to be elliptic. So if you write out this equation in coordinates, it's not elliptic. And so what it means is that we're not, we can't use our solution theory for SPDEs. There's no, there's no kind of regularization in a sense along the gauge orbits. So here we use a trick called the Dieterk trick, which was originally applied to Ricci flow, but Donaldson then applied it to look at the Yang-Mills equation. So you can add a term to make the equation elliptic by using a time-dependent gauge transformation. So basically what we're going to do is we're going to have our dynamic, but we're also going to have like a rotating reference frame. And the combination of these two will allow us to have an elliptic dynamic. So here I've written it in coordinates. I call this the SIM equation, or the stochastic Yang-Mills equation. So if you have a solution, at least formally, if you have a solution to this equation, and then you have your a time evolving gauge transformation that satisfies this equation, then if you act on the solution to this equation by the gauge transformation, that is formally you get something that solves the original dynamic, which was this one, except again, you rotate the noise. So if you didn't have a noise, you'd actually end up at the same place again. But then here you just rotate the noise. But again, we expect that the rotated noise is equal in distribution. So in some sense, this gives us a parabolic, a flow that is a lot nicer that that falls within the scope of our theory. Okay, good. So now let's talk a little bit about this equation. So this is the equation that's like the main character in the story that's coming next. So as was promised before, we have a pretty robust theory for dealing with singular SPDs now. So if you just think about this as, you can imagine you just writing this equation, this Lie algebra and this Lie group, you can just think about them as collections of matrices. You can write this as like a huge system of scalar equations driven by scalar white noises. And then you can throw the machinery of regularity structures at it. And then you just really have to care about power counting. And so if you think about the power counting or its general form, this is a perturbation of a stochastic heat equation by two nonlinearities. So we see a kind of phi-4 type nonlinearity, and then we also have this transport term. So in a certain sense, the phi-4 kind of produces a lot of renormalization, or this guy does, but this term is actually the more singular one in terms of power counting. But the picture is that it's subcritical when you're under 4 dimensions. And in 2 and 3 dimensions, you expect the solution to be a distribution, which means you need to define the nonlinearities in the renormalized sense. So again, the regularity of the solution you expect to be of the same as the free field. So in 2 dimensions, you're 0 minus, you just barely miss being a function. And in 3 dimensions, you're minus 1/2 minus. So you're quite a bit away from being a function. So, so the existing theory gives us a certain type of local well-posedness for this equation. So basically, if you look at the paper with Ilya, Avon, and Martin, we have this kind of black box theorem that just says, okay, give me the equation, here's your local existence. So basically, one way to think about that is we sort of have a local well-posedness for certain types of perturbations of a stationary free field. So that you just get for free, but that's not quite good enough. So what we're aiming for is we actually want to define this dynamic in a way where it has some sort of gauge covariance and law. And the real final aim is to define a Markov process in a space of orbits. Then, if you could kind of prove some sort of global well-posedness, then you could try to actually construct a corresponding stationary measure using a tightness argument. And so this would kind of then give you one way to attack this problem in terms of, in the framework of constructive field theory. How do we build this measure? Great. So here I kind of wrote the same equation in a kind of more compact form where I put all the terms that are not appearing in here. So when someone writes down an equation and they say, I'm going to solve it using regularity structures to give you a solution, well, there's some sort of degeneracy there. So in the theory of regularity structures, our solution theory usually gives a kind of it gives you a family of solutions that are parameterized. So if you're trying to solve this equation, then you can realize it as the limit of renormalized equations. And here, of course, sorry, I should put an epsilon here because you need to renormalize the nonlinearity. So you kind of regularize the noise. You have a smooth equation, and then the solutions to those as the limit, or actually, sorry, I did the good job. I kind of did what I was. The renormalization is here. So you kind of renormalize the equation by adding some term that could potentially diverge as you remove the regularization. But the idea is that that this renormalization prescription is only, it's the divergent part that is sort of actually fixed by the need to converge, right? So I could get another solution by just saying, okay, I'm going to renormalize in the right way, but I'm just going to add a shift. And so this gives us a one parameter family of solutions. Now, one important thing here is that these sorts of terms actually, if you just looked at the deterministic flow, would break gauge covariance. So this mass term does not transform in the right way under a gauge transformation. And in particular, what you expect is that if you use a regularization, so here, the regularization we use is the same as what many people use in singular SPDE, which is space-time mollification. But instead, if you kind of did something like discretization, where you preserve some sort of approximate gauge invariance, then what you expect is you can use ward identities, or the fact that you have this invariance, to show that you don't need any renormalization at all. But since we use regularizations that destroy gauge invariance, we produce renormalization. In particular, we expect that we do need to kind of put in these terms. So we have a one parameter family of solutions that are kind of parameterized by this order one shift. And so one way to kind of think about the first part of our goal is, can we choose this constant so that we have gauge covariance? So if we chose two pieces of initial data that are gauge equivalent, so this means that there's some gauge transformation that takes you from one to the other, so they describe the same physics, then let's start this dynamic from A, and then also start this dynamic from B. Then what we want is that basically at the level of gauge invariant observables, we want these to give us the same expectations. It shouldn't have depended whether we started from A or started from B, because they're physically equivalent. And what you could imagine is, there's a way to actually define, this is one way to do it. It's not quite the way we do it, but you could imagine you can find a gauge transformation that takes you from the guy that started from another point to the original one, okay? But the key idea here is that exhibiting an actual gauge transformation is kind of how we show gauge equivalence, or is the best way to kind of do it. So what's our argument? Well, let's imagine that we have a solution to the regularized renormalized equation with some value of the shift. So then it's possible to basically, if you're starting this dynamic from little a, then if you instead, you can define another dynamic given to you by a kind of equation like this, which has some of the same form, but there are some correction terms due to the fact that this term is not gauge covariant, along with evolving gauge transformation such that this diagram commutes, right? So I can either start from A and little a and follow the dynamic capital A, or I can translate to another point on the gauge orbit and then run the dynamic B. If I do that, if I go along this way, then there's another gauge transformation that tells me that I'm gauge equivalent to where capital A ended up. Okay, and again, here's the picture kind of in the limit, but here I sort of stuck epsilons all over the place. So this gives you another dynamic that sort of starts and ends in the place that you want to be. A place that is gauge equivalent to where capital A ended up. Sorry, I'll speed up. But what you want to do is you want to show that this other path that you defined, that as a dynamic actually has the same law as this dynamic if you would have started from B. And so how we do that is we sort of compare this dynamic with something that is basically more explicitly seen to have the same law as the original dynamic. And so what's the difference between these two equations? Well, here you regularize the noise and then you rotate. And here you basically rotate the noise and then you regularize. And so why this is different is basically, I mean, the reason that in some sense we've broken these invariances is that our regularization does not preserve the Ito isometry that allows you to see that this does not have the same law as just the original regularized noise. And so the game that we play is we try to find a unique, or try to find a value, sorry, there's no bar here. You try to find the value of this C so that basically three things hold. So the first thing is you need to make sure that our argument is we show that this equation and this equation actually have the same limiting solution theory. So the solution maps to this guy and this guy are actually the same pathwise as epsilon goes to 0. That introduces some constraints in these renormalizations. The other thing we want to do is we need A bar to be renormalized like this because we want these guys to be equal in law before we send epsilon to 0. And then this equation really needs to have this form because it needs to be pathwise the image of A under a gauge transformation like this. So we sort of have two pathwise relationships and then one relationship in law, which introduce constraints on how we renormalize. Because what you're worried about is, maybe this guy is renormalized incorrectly to converge, or this guy is renormalized incorrectly to converge. So what you expect is that this term will produce new renormalization. And what's somehow miraculous is that the renormalization that is produced by this multiplicative term in some sense is not so different than the mass renormalization, which produces a cancellation of divergent parts. In 2 dimensions, this can actually be done explicitly by calculating the renormalization constants. In 3 dimensions, the number of trees becomes quite large. And what we have to do is we have to use soft arguments that leverage certain stability and injectivity properties of our solution theory. So the kind of some of the arguments here are very similar to those used to prove certain properties for the geometric KPZ equation. Good. So finally, I'll close with the state space. So we want to, so what we want to do is we would want to actually think about this dynamic as being an evolution in a space where we can actually define gauge invariant observables like these Wilson loops. And it would be great if we actually had a quotient space of orbits where we could take a quotient dynamic. The problem with defining holonomies here is that our connections, are going to have the same regularity as the stochastic heat equation. They're going to be distributions. So, so what you can show is, you can very carefully define certain subspaces of distributions that have that have special properties. So these are kind of one forms with some sort of kind of additional holder type quantities, and you can do this. So basically, this construction works when you expect your gauge field to have regularity better than -1/3. And what these distributional one forms accommodate is they allow you to define holonomies as continuous, well-defined functionals. You have a continuous group action of a gauge group on this space. And the quotient space is actually a polar space. And the kind of elements of this quotient space, or the orbits, are really characterized by these observables. And I want to say that these spaces are kind of very similar to spaces that Ilya came up with in earlier work. So in D = 2, the free field is just under 0. So this allows us to actually define a Markov process on this orbit space. There's additional work, right? So basically, we know that our dynamic takes values in a C alpha space, but we wanted to actually take values here. So here we have to use the fact that we can actually realize it as a free field plus something singular, and so that the free field lives in this special space. But all of that can be done. In 3 dimensions, you're not borderline. You missed the mark by quite a bit. And so you can partially circumvent this problem by trying to regularize. So you can define a new equivalence relation by saying that 2 distributional gauge distributional connections are equivalent if you can find some time such that if you evolve them under the deterministic Yang-Mills heat flow, which is regularizing, then they're gauge equivalent in the classical sense. So here, there's a kind of painful thing, which is you have a notion of gauge equivalence where you don't have a gauge transformation anymore in some sense, not in the same sense. So this is, this gives you a bit less, but yeah, and that's the 3-dimensional story is still a work in progress but nearing completion. Thanks. Sorry for taking a few minutes extra, and thanks for listening.
So thank you, AJ. No problem going a bit over time. So we have plenty of time. And then now we move on to the discussion by Ilya. So please, if you could share your screen.
Yes, sure. Okay.
Okay, it looks okay. So please.
Yes. You can see that? Yes. Okay.
Yes.
Good.
Yes. You can see.
Okay. Yes. Great. Okay. So thank you, AJ, for the very nice talk. It was a nice presentation of the work. Better than I think I could have done. And also thank you for the invitation to be here as a discussant. It's a bit maybe unusual to be a discussant as a co-author on the paper, but I'll try to do my best. So what I wanted to do was just to discuss some other approaches to quantum Yang-Mills that have been out there, in addition to the stochastic quantization picture. Some of these approaches AJ mentioned as well. So I wanted to give a little bit more detail about them. So in 2 dimensions, there's a very nice thing that happens. So one has an exact solvability property for 2-dimensional Yang-Mills. This has been sort of around in the physics literature, at least since the 70s, maybe even earlier. So Migdal and Polyakov looked at these problems. In the mathematics literature, they were kind of the earliest kind of complete works that gave a nice answer. Are 2 papers by Gross, King, Segupta, and by Driver, both from 89. And then this idea was taken up later by Sengupta for back in the 90s. So in a couple of publications in the 90s. And so both of these papers, they work with R2, so on the whole plane. And then this paper of Sengupta, it works on an arbitrary, say, compact manifold. And both of them leverage something called the axial gauge, which I'll describe in a second. And then there's another approach also for 2 dimensions, and also actually for compact surface M. And this is an approach by discrete approximations by Levy. I'll also try to describe that in a little bit of detail. And then, so these approaches are really restricted to 2 dimensions, where you have very nice solvability properties. So this is all under here. So what I mean by solvability properties is that you can really explicitly write down what gauge invariant observable should be. So as a random variable for say, one fixed loop or some finite collection of loops. Okay, and then in 3 and 4 dimensions, you unfortunately lose this very nice exact solvability property. So you have to appeal to other methods. And so sort of the state of the art in this in these works are a work by Balaban, which is quite famous. It's from the 80s and it uses a renormalization group approach for the lattice. And then there's another approach which is in essence similar in spirit. It also uses renormalization group ideas, but it works in the continuum. This was done by Manière, Vassaux, and Seigneur in the early 90s. These are both renormalization groups. And they both work in 3 and 4 dimensions and 2 dimensions as well. Okay, so I'll describe sort of what each one of these approaches now gives you as an output, and maybe give a comparison at the end between them and also with the approach that AJ described. So for the first approach and the axial gauge, this one I'll spend probably the most time describing because it really demonstrates why 2-dimensional Yang-Mills is quite special. Okay, recall that there were these one forms that we were looking at. So one forms were essentially functions from, so let's work on R2. So there's no, in some sense, R2 is a bit simpler than something like the torus because it has no topological obstruction. So there's no loops kind of, if you go in one direction, you never come back to yourself. So R2 in some sense is actually a bit simpler. So let's look at R2 for the moment. So one form is written essentially as a function from R2 into G2. G is the Lie algebra that we're working with. And recall that we're only really interested in gauge orbits. So we're not really interested in the one form itself. We're interested in a one form when we hit it by gauge transformations. So gauge transformations, recall, are these functions from R2 into the Lie group G that we're interested in. And gauge transformations take, they kind of look like this. So you hit A with the adjoint of G, and then you subtract a certain derivative of G. So these gauge transformations are kind of seen as automorphisms of the principal bundle that you consider. In some sense, they can be seen as coordinate transformations. So when you think of them as coordinate transformations, it makes sense that you only really care about a connection modulo the way that you write it in coordinates. And so what's quite special in 2 dimensions, and say even on R2 in particular, is that every one form has a very nice axial gauge representative. So what it means is that you can always find a gauge transformation, no matter what one form you take, such that its first component is just identically 0. So this you can get sort of this identity. And then the second component is 0 on some one-dimensional subspace. So for example, on the y-axis. So here you can get this equality here. And the way to see that is actually not very difficult. So when you look at how gauge transformations act on one forms, you sort of see that you essentially just need to solve ODEs. So you first look at your y-axis and you solve the ODE for G, which tells you that this A to the G along the y-axis should be 0. And then you solve along all the horizontal lines on R2, kind of going backwards and forwards. And so essentially you're just solving families of ODEs when you derive this axial gauge. So this is, it's quite nice that you can actually do this. So what's not very difficult to see is that if you start with your original Yang-Mills measure, and then you put every one form in your expression into this axial gauge, then you don't pick up a Jacobian factor when you do this kind of restriction or a change of coordinates, essentially. So there's no, it has a constant Jacobian factor, would be the correct thing to say. So when you write out the Yang-Mills measure in the axial gauge, I've called this mu tilde here. So remember that it was given by this, it was given by this kind of Gibbs type measure for the Yang-Mills action, which is the L2 norm of the curvature. But if the first component, so recall that the curvature is something that looks like this. So say partial 1A2 minus partial 1 plus the bracket between them. So the coordinates, it looks like this. Well, if your first component is identically 0, then this vanishes and this vanishes, and you're only left with partial 1A2. And so your measure essentially becomes something that looks like now like a Gaussian measure. So you've killed off all the nonlinearities which are non-quadratic. And so this is quite a remarkable thing that happens in 2D. So this gives you essentially gives you a distribution on R2, which looks like so the interpretation of this is that A2 should be like partial 1 inverse of a white noise, Lie algebra valued white noise. So okay, so this is a perfectly fine representative of the Yang-Mills measure as a distribution. So some features of this is that it actually yields suboptimal regularity. So this object actually becomes in C minus 1/2 minus if you compute the regularities, but you expect actually something in C0 minus, because that's where the Gaussian free field lives. And relatedly to this, gauge invariant observables aren't defined pathwise for this kind of distribution measure. So you need to use Ito calculus to define Wilson loops. So this approach was developed, as I said, by Driver, Sengupta, and others in the 80s and 90s. Okay, so then moving on to the second approach, which is the one by Levy. So here one starts rather with discrete approximations. So maybe on some sort of a lattice or a finite graph. Your discrete approximation of the Yang-Mills measure is a probability measure on functions from the edges into the group. So I've written this the wrong way around. Function from the edge, from the group from the edges into the group. And you should think of the value of this function at a particular edge as the holonomy along this edge. And so the remarkable thing about this here, and this is a kind of a manifestation of the solvability of Yang-Mills in 2D in a kind of a different light, is that you can define this approximation. It's known as the Villain action approximation in such a way that the holonomies for this discrete measure, which is perfectly well defined. This is kind of like you should think of this space GE as just a compact manifold. So this is just a probability measure in a compact manifold. It gives you exactly the correct holonomies that agree with the Yang-Mills, with the continuum Yang-Mills measure. So it agrees entirely with the continuum Yang-Mills holonomies, provided that you look at loops inside of the graph. So basically, if you just fix a loop here, like say, let's look at this one here, then the holonomy around this loop, so that the product of these group elements along these edges will kind of be invariant when you take subdivisions of the graph. So, what that ultimately gives you is it gives you kind of a projective system of probability measures when you kind of embed graphs into each other and take the refinements. So once you have this very nice projective system, you can take the continuum limit, and the ultimate outcome is kind of vaguely speaking can be said as it gives you a stochastic process which is indexed by Wilson loops. So it gives you a way of describing the Yang-Mills measure through gauge invariant observables. So, so features of this system is that you forget entirely about the one form A, because you just sort of you only look at it through these gauge invariant functions. And another nice kind of thing that ties in with actually a little bit of free probability is that the holonomy around a particular loop L, this is the loop L. So the holonomy around every loop L is given by quite a nice formula, which is that you run a Brownian motion on your Lie group until you hit the area of, and then you look at it at time, which is given by the area of this loop. And then this is the kind of the random variable given given this holonomy. So this is a very nice formula. At least, okay, this is true on R2. For other surfaces, there's a correction to this. But morally speaking, it's like this. Okay, so okay, so this is the story in 2 dimensions. Okay, so then in the difficulty in extending the previous 2 methods to 1 and 2 from 2 dimensions to 3 dimensions is that there were kind of a gauge invariant observables that you were looking at were Wilson loops, and as AJ mentioned, the Wilson loops are ill-defined in 3 dimensions, so it's not clear how to write it out as some sort of stochastic process indexed by loops anymore in 3D. So I'll speak just very briefly about these other RG approaches, and partly very briefly because there's not much time, but also because I don't understand them very well myself. But the very basic concept of the renormalization group approach is that you start off with your action functional on some very fine lattice, and then you coarsen your lattice out. So what I mean by coarsening it out is that you integrate over small fluctuations inside some of these cubes. And then essentially, once you've integrated over the fluctuations inside your group, you get an effective action on a kind of a coarser lattice. So you move from a very fine lattice to a slightly coarser lattice. And then you kind of do the same here. So then you average over all the fluctuations in here to give you an even coarser lattice. And what happens is that your action then transforms as you're doing this. So imagine that you're trying to compute some quantity, which is like the characteristic function of the curvature. So J here is like a source term. And then, so you start off with your original action, you transform it to another kind of action on a coarse lattice, and then you keep doing this until you hit order 1 spacing for the lattice. And this gives you just some number. And then the goal is that you want to show that you can change your action in such a way. So this is where it's sort of counter terms and renormalization enters. That these types of characteristic functions, they converge as you send the spacing of your original lattice epsilon to 0. This is the kind of the ultimate goal. So you want to basically to construct these so-called Schwinger functions. Okay, and then this approach so this was the kind of the sketch that I made here was the kind of the picture of Balaban, and then this final work is similar, but it's in the continuum. And so the outcomes of these is that it gives you stability. So it gives you kind of compactness of these, well, with some good faith, it gives you compactness of the measures in finite volume. And so it might give you compactness in like some Sobolev space like H-1. But it doesn't give you an exact limit. So it doesn't give you that it actually converges to something. And it doesn't actually give you any information about gauge invariant observables. These really work in like a very linear space. So in contrast to the first 2 approaches, the one form is kind of the key player here. And so what kind of just want to say that perhaps this approach of stochastic quantization that AJ described is maybe somehow in between these 2 approaches. So it uses, so because you kind of have these singular products and require renormalization, it uses a bit of similar ideas to these renormalization group approaches. But at the same time, it's perhaps retains a little bit of the geometry of the original problem. So you kind of these dynamics there. They kind of really retain gauge invariance and gauge covariance, and you can really make that precise, which is, I think, not well. Okay, I won't say that that's not the case for the third and fourth approaches, but in my mind, it's a little bit clearer at least. Okay, and so I think I've run out of time. So I have maybe one quick question for AJ. Just again, a bit awkward asking it because this is a joint work with him, but something that has often been puzzling me, and I've never asked this. So you mentioned that there's these approaches by regularization of modification, which is very common in single SPDs, and also by discrete approximations like this work of Levy. So when reading works by kind of renormalization group in physics, there's a very popular approach, which is this dimension regularization, which they claim is really doesn't break gauge covariance in any way. So my question is, do you know anything about this? And is it possible to actually somehow combine these ideas in any sort of way?
Oh yeah, so thanks. Yeah, thanks to that nice overview of a pretty difficult but like beautiful program to kind of understand these models. Yeah, so dimensional regularization. I would say that we have to my sense is that we have to understand phi-4 first. And I think, as far as I can tell, maybe someone can correct me, but no one's really shown me, like, I've never seen dimensional regularization done in a kind of probabilistic manner, right? So I've seen, basically, I've seen like dimensional regularization done like at the level of observables. Like so the kind of closest thing I know of for like phi-4 is, an attempt to kind of do regularization around the critical dimension by working with a fractional Laplacian. So you can kind of try to use the strength of the Laplacian as a parameter. But then the problem is that, and that's kind of mathematically well defined, you have a nice model and everything, but then it turns out that you don't capture you're capturing something else. So I think the kind of honest, I think that is really interesting. I think kind of the step zero to that is, as homework, is we need to even understand dimensional regularization for something like phi-4 first. Yeah.
Okay. That makes sense. Okay, thank you. Are there any other questions?
Yeah.